20,000 spectrum across the chromatographic run. Okay, we couldn't handle the problem. We found out we could only handle 7 seconds of FT data at full blast before we filled a typical 200 gig hard drive. So we ran this problem. The way we solved it is we dump the majority of your data. We don't smooth it. We don't transform it. We dump it.
So is it just a cross-leading or a
So what we do is we have enough resolution that we can look at peak shape, and we know what the spacing between peaks should be, right? If it's either got to be 1, a half, a quarter, a third, depending upon the charge state. So we look at those and we determine when the spacing is just random crap, okay? Based upon knowing what an isotopic pattern looks like. If we see that, we just dump the data, which is why if you ever look at an FT spectrum, the IT, no matter where you drag, you'll always see some peaks. Okay? With the FT, it is not uncommon to drag across the peak and see a ton of data points, and then drag where there was no significant peak and not see just small grass. You'll see nothing, because we've dumped out the data completely. It's gone to 0. This is how we take a 2 gigabyte file for one spectrum down to 37 kilobytes per spectrum.
So why is it not an alternative just to take that full data and centroid it, because that'll drop down? Obviously centroiding.
Because centroid is even better yet, but people don't believe centroid data on an FT. All I ever run is centroid data on my LTQ. The minute you throw an FT up, people want to see where's my peak width. Okay, people associate centroiding with resolution. Can't centroid. Okay, there's nothing wrong with centroiding because we centroid properly. Okay, that would be even better. Right. Most people don't believe that though. If they're using high resolution, they want to see peak shape. Which ones I've never seen anyone use the peak shape for information, but they want to see it. So we're always pushed. It's got to be profile mode data. Okay, just a little. I don't think there's any scientific reasons. It's more historical.
Because we've run profile centroid, we don't find more phosphorylation sites with either one. So
no. We probably run centroid, right?
Why waste the hard drive?
Yeah, I agree totally. Most people will disagree with you saying if it's an FT, it's got to be profile mode data. Okay. Cool. Questions, thoughts, or comments on this? No questions, thoughts, or comments?
So if the ion, the relation, the function between the ions will affect the current you accept, you receive the signal, can you define the? I mean, there are some reaction between each other. So how can you know the exact frequency of when ion or
Yeah, how do you eliminate space charge once it's occurred? Because it's in any complex mixture, it's going to be ions passing by.
Just run a low ion population so your pure perturbation is below what you're looking for mass accuracy. Okay. We can't control space charge actively. Okay, this would be our ultimate goal. Our ultimate goal would be able to somehow look at what's eluting and adjust the population to give you the best dynamic range without space charge. Can't do that. It's a fixed concept. You always tell us how many ions in the cell you want. AGC regulates to give it in your FT just like it does in the LTQ. Okay. If you have a complex mixture eluting and you're at a high population, you're going to space charge. And you're not going to get that low mass accuracy you're looking for. Okay. So it's a choice you make as a researcher. Do I want more? And it's not sensitivity. Not sensitivity you're gaining. It's dynamic range you're gaining. You're gaining the fact that if a complex mixture is eluting, what's the highest ratio I can get between the tallest peak and the smallest peak? Okay? That's the key. It's dynamic range. People keep using the word sensitivity. That's the wrong word. It's dynamic range. Okay? Higher ion populations don't give you higher sensitivity. They give you higher dynamic range of co-eluting species. Okay? Higher sensitivity is ion optics and nanospray in chromatography. Okay, and that's how we get higher sensitivity. Higher dynamic range we get because of using higher ion populations. Okay, if you have a setting of 500,000, okay, which is really probably 10,000 ions, actual measured ions, because it's about 50-to-1 ratio, okay, your dynamic range is inherently, I wouldn't say 10,000 even, I'd probably say like 3,000. You probably need at least 2 or 3 ions in that little thing to get a decent peak that you can measure. If you bump it up to 1,000,000, so now you're really dealing with 100,000 ions, now your dynamic range can go up by almost an order of magnitude, so you can see a lot smaller peak and get an MSMS of him.
Is it linear with that value, the AGC?
No.
So it's because of the space trend?
It hits a limit. Okay. Gigi was operating up at 66.
66?
6 million ions.
But with the short IT there?
With a short IT. Even with a long IT, it wasn't linear. The problem is when your IT time gets really large to handle these large populations, when the ions come in, some of the ions pop back out. If you're having this damn ICR cell open for a second and a half, you start to lose them back out. I find 1 to 3 E6 is probably your upper limits.
Yeah, so are they pulsed in, or it's just one open the door for, like if I said 1,000 milliseconds or 1 second for the IT?
And you're at the right population so that it takes 1 second to fill, it just opens and comes in and closes.
So that's basically the time that the door is open?
Yep, that's all it is, the time there's the door open. Okay, we don't compress the ions or anything.
How close are we to things bouncing back out? I mean, we did 5 milliseconds, everything would bounce out, right? Or 5 seconds.
I think you're going to start losing things. It's not totally linear. You're not going to lose like a ton.
How fast are things traveling around?
Oh, the flight times. The flight times are...
But once from when the first peptides come to
the packet width.
Yeah.
Oh, the packet width is only 100 microseconds, maybe.
Well,
It's small. It's not like the packet streams, It's just sometimes when you have a very small amount. You have to trap them for a real long time. Now remember, it's not the FT that's opening and closing. That's constant. It's the ICR it's the LTQ that's trapping for long periods of time. Okay, the trapping happens on the LTQ.
pulse fill the
Right.
trap, and then you just send it all back.
And then you just dump it down. So it's not the ICR cell that's staying open for long periods of time. The ICR cell is open for the flight time based length of time. It's the ICR cell that's filling up. Okay, you got that in your head? The AGC is always on the linear trap. Okay. Cool.
So why is there sitting an AGC on the FT then? That's the amount of time it's open?
It's still the amount of time the linear trap's open, but there's an AGC for the linear trap, which is if you're doing full MS on the linear. There's an AGC for the FT, which is when you're doing full MS on the FT, but you've trapped them in the LTQ. So you trap them, you cool them, you send them down.
So that's an amount of time that includes the time it's not separate deconvoluted from the LT. So say I set it at 1,000,000 and I set it at 1 second. Would all those ions be accumulated first in ion trap and then all be passed out?
Correct. Okay.
So changing the AGC on the FT changes what?
The amount of time that the linear opens to fill up prior to drop into the FT. Is everyone with me?
So why does that increase your dynamic range?
Because you have
Increases
more
the range of what?
you have more ions to begin with. Okay. So when they're measured,
That's not dependent on it, because that's only dependent on the linear trap AGC. So the FT
AGC is always on the linear. It doesn't. There's
So
two
there's
different
two
numbers.
values.
There's two different values, but it's done exactly the same way in exactly the same spot. It's not like there's a different set of electronics to do
When they
AGC.
draw the diagram,
It looks like they're AGCing on